Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at phenol, so the structures and the reactions of phenol. At the very end of the video we'll also be looking at the directing effect of certain substituent groups which are attached to benzene. Okay, so if you're only looking for that bit you can skip right to the end. Otherwise I'd like you to open up your booklets and we'll get started. Okay, so phenol. So the structure of phenol is, it has a benzene ring with an OH attached, which means our structural formula is C6H5OH. It's my benzene ring, this is my OH attached here, and the molecular formula of phenol is C6H6O. So when we're talking about phenol, the position of the OH group is always on carbon number 1, irrespective of what else we have attached to this phenol. So some examples of compounds containing phenol. So I'm going to draw them, been copying them down, and then I'd like you to have a go at naming them. So phenol with 3 chlorines attached. Phenol with 2 methyl groups attached, and lastly, let's do it in a different position. And finally this one. Okay, so I'd like you to have a go at naming these. I'll give you a couple of minutes, then we'll go through the answers. Okay, I'm sure you've all worked this out. So we know that the OH on the phenol is always number 1, so we don't have to put it as 1. So this would be called 2,4,6 tri, because there's 3 of them, chlorophenol. And this is actually used as an antiseptic. And you've probably seen it abbreviated to TCP, so it has a distinctive smell. Next one, 2,4-dimethyl, because we have 2 methyl groups attached in the positions 1, 2 and 4. 2, 3, 4, oops, excuse me. It helps if I do it right. 2, so 2, 3, 4, 5. Now 4. And finally, we have, well, this is so a bit more tricky. We have the OH not at the top here. So this is really the conventional way we draw phenol, but it could be drawn like this. So this is my first carbon. So it would be 2 bromo, 3, 4, 5, 5 methyl phenol. Okay, so moving on. So physical properties of phenol. So phenol is a white solid at room temperature. Unlike benzene, which is a liquid at room temperature. The high melting point of phenol is due to the stronger hydrogen bonds that are present in phenol along with the weaker London forces. Okay, so you should know how to draw hydrogen bonding, so I want you to have a go at doing this as well. Okay, I'm sure everyone's diagram looks like this. So the things you have to remember are, you have to include your dipoles, delta plus and delta minus. And you have to include your lone pairs, so my lone pairs on the oxygen. Then you've got to show the hydrogen bond and clearly label it. Okay, so this is what your diagram should look like. So moving on. So the hydrogen bond requires more energy. Energy to overcome, and therefore phenol has a higher melting point of about 40 degrees Celsius compared to benzene. Okay, and phenol is relatively soluble in water. You might see this described as partially soluble in water, and this is due to phenol being able to form, again, as you probably guessed, hydrogen bonds with water. Okay, so again, I want you to draw the hydrogen bond between a phenol molecule and a water molecule. Okay. Okay, I'm sure everyone's drawn this. So I've drawn my water molecule here. Again, I need my dipoles, I need my lone pairs on both my phenol and my water molecule, and then clearly showing my hydrogen bond between the water molecule of the H on the water molecule and the lone pair on the phenol molecule. Okay, so moving on. So reactions of phenol. So phenol generally undergoes two types of reactions, and you need to know both of them. So first one is reactions involving the delocalized pi system or ring. So I will use this interchangeably, pi ring and pi system. It means the same thing. This is the circle in the middle of the benzene, well, the phenol, remember. And two, reactions involving the OH bond. Okay, so we've got two types of reactions. One involving the OH bond and one involving this, the P delocalized system. Okay, so we will start with the ring reactions of phenol. So phenol undergoes electrophilic substitution reactions. Just about squeezed it in. Similar to that of benzene. However, it is much more reactive than benzene. So phenol is more reactive than benzene. This means that reaction conditions are a lot milder compared to benzene, e.g., so we can carry out reactions at lower temperatures. Okay, so if you're unsure about the electrophilic substitution mechanism, I suggest you go back and look at the benzene video that I made, okay, before we move on. Okay, so why is phenol more reactive? Well, it's to do with the effect of the OH group. So there are two lone pairs on the O in phenol, and one of the lone pairs delocalizes into the benzene ring. Okay, so I will show you what is happening. So here are our carbons, here is our oxygen. Really, we should have a hydrogen attached here as well because we're showing our phenol, but I'm not going to do that just yet. Okay, so in each of these carbons we have p orbitals. Don't know what happened then. Let's try again. Until I didn't take art at school. Okay, and we also have p orbitals on our oxygen. So what happens is that all of these p orbitals overlap. So we have overlap of p orbitals, which means we extend this pi delocalized system by including two lone pairs on the one lone pair on the oxygen. Okay, so we've overlapped with these p orbitals, and we've included this overlap with the oxygen p orbital as well, of a lone pair. So that means that now we have an extended pi delocalized system. Okay, so what does that mean for our reactivity? So we'll now move on to filling this out. So this means that there are now more electrons in the delocalized pi system, or pi ring. So I'll just put / pi system or pi ring. This increases the electron density in the pi system, which makes sense. We've got more electrons in the system, so the electron density is increased. This is known as activating the ring. Okay, it's just a phrase you need to remember. So if the electron density increases, it means electrophiles are more attracted to the ring, and hence phenol undergoes substitution reactions much more readily than benzene. Okay, which makes sense. Yep. So the delocalization of a lone pair into the pi system leads to the phenoxide ion, which is when we have lost the H+, it becomes more stable. And also the OH bond becomes weaker. So phenol is able to donate a H+ and act as an acid. Okay, so that's important when we come on to our reactions involving the OH group. Okay, so moving on. So I'm just going to write, actually, just so you don't get confused. Let's put reactions involving OH. Okay, moving on. So, phenol and halogenation. Okay, so what happens is that we are talking about reactions involving the ring, and it's an electrophilic substitution reaction, exactly the same as what happens mechanism-wise with benzene. However, because phenol is more reactive, we get multiple substitutions to produce this. Conditions happens at room temperature. The reagents are phenol and bromine water. So this bromine is aqueous, and the observation, we get an observation, we see a white precipitate. So this is actually a test, a qualitative test to work out whether a solution or something contains phenol. We have bromine water, and if we get a white precipitate, it means that phenol is present. Okay, so very quickly, I'd just like you to name this product. Okay, and I'm sure you've all been able to name this as 2,4,6-tribromophenol. Okay, so moving on, this is our halogenation reaction. We will now move on to phenol and nitration. Right, so we take our phenol. Nitration, as you probably know from looking at watching the benzene video, is when we add an NO2 onto the benzene ring. And what we actually get produced is a bit of a mixture of two things. So these two things. Okay, I just want you to have a look at this and see if this is correct. Okay, I'm sure you noticed that it's not balanced, so we need 2 phenols and 2 nitric acids, and we produced these 2 things. Okay, this is called Oh no, I'll actually get you to do this. So I want you to name this one and this one. Okay, I'll give you a minute. Again, I'm sure you've all worked this out. So we get 2 nitrophenol and 4 nitrophenol. So we actually get a mixture of products produced. Okay, so conditions. So as we said, because phenol is more reactive than benzene, this will occur at room temperature. We obviously need phenol as one of our reagents, plus aqueous nitric acid. So the nitric acid does not need to be concentrated, unlike in benzene where it does, and we have to have a mixture. We can just use aqueous nitric acid. Okay, so moving on. So phenol does not require high temperature or concentrated reagents or a catalyst, unlike benzene. So just put in brackets for reactions to occur. And actually, if we did use concentrated nitric acid, we can get multiple substitutions. E.g., so if I use phenol and concentrated nitric acid, we could get multiple substitutions such as this, which would be 2,4, 6 nitrophenol, excuse me, plus 3 H2O and 3 HNO3. And as I just said, I know you can work this out yourself, so we'll just write this down. 2,4,6 tri nitrophenol could be produced. So depending on whether we've got concentrated or aqueous nitric acid, we're going to get different products produced. Okay, so we will move on. So we've talked about so far the reactions involving the pi system, yeah, and they've been electrophilic substitution reactions. However, you can have a different type of reaction, which is reactions involving the OH group. Okay, so the effect on the OH group. So due to the delocalization of one lone pair on the oxygen atom into the ring, the negative charge on the oxygen atom decreases. This means that the strength of the OH bond decreases, which we've already mentioned previously. Okay, so what happens is so my electrons are pulled towards my benzene ring, my pi delocalized system. That's what we said, that one pair delocalizes into this system, which means that it weakens the OH bond. So this OH bond is weakened. This is important when we're talking about the acidity of phenol and the reactions. So phenol and acidity. Phenol is a weak acid and can partially dissociate to produce H+ ions due to the weakened strength of the OH bonds. Okay, and we could show that as I have my phenol, and if it's behaving against an acid, it must donate a H+. Because it's a weak acid, it's only going to be partially dissociate to produce this. And we have this produced, and we call this the phenoxide ion. Okay, So the reason why this happens, as we've just explained, is because of the weakening of the OH bond due to one of the lone pairs delocalizing into the pi system. Okay, so it can behave as a weak acid. So phenol undergoes generic acid-base reactions with the exception of a reaction with a metal carbonate. Now you should be very familiar with acid and alkali and metal reactions, so I'm going to get you to do most of this filling out. So first of all, I would like you to have a go at filling this out. So I've given you the chemical reaction here. Yep, so I need to fill out the generic word equation and below the chemical equation. Okay, and I'll give you 5 minutes. Okay, and I'm sure you've all got this. I was a little bit naughty and I forgot to tell you that you'd need to balance this equation here as well. So my chemical reaction would be 2 phenol plus 2 sodium would form 2 sodium phenoxides plus hydrogen gas. And last point to notice is that if we're doing this acid and metal reaction, the metal must be reactive. So, such as sodium. Okay, so now you've got the idea, I'd like you to have a go at doing this. So fill out the generic equation, and this time do the second bit, so this bit. I've given you this, the chemical equation at the bottom. Okay, I'll give you another couple of minutes. Okay, I'm sure you've been able to work this out as long as you knew your generic equation. So acid plus alkali forms salt plus water. So this would be my equation, and it's already balanced, so that's easy for you. Okay, so moving on. So we said that metal carbonate, a phenol isn't a strong enough acid to react with a metal carbonate, so here we would have no reaction. Okay, so moving on. So we've talked about the phenol behaving as a weak acid. It can also be involved in esterification reactions. Okay, now to do this, we can react phenol with either an acyl chloride or an acid and hydride. I will give you the generic equation. So my acyl chloride would look like this, and my acid and hydride would look like this. Oops, no it would not. Let's do it correct. My acid and hydride would look like this. Remember, the R group stands for an unknown carbon chain. So acyl chloride has a C double bond O and Cl. It looks very similar to a carboxylic acid, but we replace the OH with the Cl. And an acid anhydride is basically 2 carboxylic acids that have been joined together. If you're unsure about these two, watch the next video and I talk about these in more detail. Okay, so moving on. So to produce an ester using phenol and a carboxylic acid, is too slow, and this is because the phenol is not a good nucleophile, has a negative charge on the oxygen atom, decreases, oops, I haven't left enough space, as electrons are delocalized into the ring as electrons are delocalized as one lone pair of electrons. Electrons are delocalized into the ring. So we're repeating ourselves. We keep repeating this business that the lone pairs are going into the ring. Normally, when we've talked about making an ester before, we've said we've used an alcohol and a carboxylic acid. Now, phenol has an OH group, so technically it could be used to form an ester, but it's so slow that if we're using phenol, we need to use something else if we want to form an ester. Okay, and what we can use is an acyl chloride and an acid anhydride. Okay, so we've got phenol plus acyl chloride and an ester plus hydrogen gas. So I would like you to see if you can fill out the equation here. So I've given you the generic equation at the top, and at the bottom I've given you phenol plus ethanoyl chloride. So you're going to have to figure out the structure of ethanol chloride, see if you can figure out what ester we produce. Okay, I'll give you 5 minutes. Okay, you might be able to figure this out. I hope you have. So our phenol is really reacting as an alcohol, and we produce an ester here. Yeah, so this is my ester group here. And my phenol is where I'd normally place my alcohol. Therefore, when we're naming it, we name the phenol in place of the alcohol. So this would be called phenyl ethanoate plus hydrogen chloride gas. Acyl chloride, it's ethanol chloride, so I assume you'd probably figure out that you need 2 carbons because it's F, so it'd look like this. Okay, and our conditions. So conditions is room temperature and pressure. We can just fill this bit out as well then. So therefore phenol and an acyl chloride is used. Okay, so hopefully you got the idea, because you're going to have another go at it. So next one, so phenol plus acid anhydride. I'll give you the generic formula again, equation. So it forms an ester plus carboxylic acid. And below here I've given you ethanoic anhydride. Okay, so again, have a go at doing this, see if you can come up with an answer. Okay, so the only difficult thing is trying to figure out your ethanoic anhydride. Yep, so it's 2 ethanoic acids joined together using this O. So we form an ester, and unsurprisingly, we're going to use one part of our anhydride to form phenyl ethanoate again, or ethanoate, so phenyl ethanoate, which means that we're left over with ethanoic acid. Okay, so you take your acid anhydride and you're left over with a carboxylic acid. Okay, conditions, this happens at a room temperature. And we can say we can also use phenol and an acid anhydride to produce an ester and a carboxylic acid, which is what we have just shown. Okay, so moving on. So the acidity of alcohols, phenol and carboxylic acids. So I've got my alcohol, I have my phenol, and I have my carboxylic acid. Well, they're all ethanol, so let's use this as ethanol as well. They're all 2 carbons, sorry. So I have ethanol, no they're not. Okay, so they're obviously not with this C6H5OH. Anyway, the point is that as we go this way, the acidity in increases. So that's the point. So alcohols aren't very acidic. Oh, phenols are weakly acidic, and then ethanoic acid or the carboxylic acids are more acidic, but they're still considered weak acids. Oh, that's a very good explanation. Hope you know what I meant. So maybe we'll just write this. So alcohols are very weakly acidic and will not react with a metal carbonate or an aqueous base. So they will react with a very reactive metal such as sodium. This is because the carbon chain is electron releasing, and this means that the charge on the oxygen atom increases. Sorry, there shouldn't be a gap there. That's why I was getting confused. Let's go back. So this means the charge on the oxygen atom increases. Okay, my computer's just frozen, so I'm just going to put you on pause for a second. I'll be back in a second. Okay, so I had a temporary malfunction of the computer. Looks like we're back up and running. So, alcohols are very weakly acidic and will not react with a metal carbonate or an aqueous base. This is because the carbon chain is electron releasing, and this means the charge on the oxygen atom increases, strengthening the OH bond. Therefore the H cannot easily or as easily dissociate. Okay, so we'll leave this gap here. I'm going to come back to drawing something here, but we'll talk about carboxylic acids. So why are they more acidic than alcohols? So carboxylic acids are weak acids, but stronger than phenol. They can react with metal carbonate, with metals and metal carbonates and aqueous alkalis. And this is because the electrons between the CCO group this is because the electrons between the C double bond O group partially delocalize to form, there shouldn't be a gap here, just get rid of it, delocalize to form a pi bond, like in phenol. This weakens the OH bond, making it easier to remove a H plus ion. E.g., so a carboxylic acid looks like this. What actually starts to occur is we get partial delocalization between this oxygen and this oxygen here. So we have a negative charge in the middle, which means that this bond weakens. So it weakens bond, which means it's a lot easier to remove my H+. Therefore, it's a stronger acid than phenol. even though it's still a weak acid. Okay, so I said we were going to do the electron withdrawing group, but I think actually I'm going to use that as a separate video. Okay, so I hope that was useful. There's no questions at the end of this because we've been doing the questions throughout the video. Okay, so again, I hope that was useful, and I will see you next time. Okay, bye bye.